Hello, everybody, and welcome to Addressing Student Stumbling Blocks in Middle School Mathematics, a look at rational numbers. I would like to introduce you to your very first speaker for today. He is the Associate Research Analyst for REL Appalachia, Mr. Christopher Sun. Mr. Sun, you have the floor.
Great. Thank you so much. Good afternoon, everybody. My name is Christopher Sun. I am a researcher with REL Appalachia. I wanted to briefly give an introduction to the Regional Education Lab and some of the work that we're doing, particularly in Virginia. The REL is a U.S. Department of Education funded initiative through the Institute of Education Sciences. We work with stakeholders, educators, and researchers in applied research and evaluation, technical support, information sharing, and dissemination. Most of our work comes through research alliances, and the Virginia Alliance that I'll be talking about in a minute is one of them. It's a partnership between education stakeholders and REL Appalachia as a way to carry out research and technical assistance in areas of interest for stakeholders. What brings us here today is the Virginia Middle School Research Alliance. We have a lot of counties that we work with in Virginia, particularly around college and career readiness, as well as early warning dropout systems. And the Virginia Middle School Research Alliance is composed of various counties in the district looking to assist middle school practitioners in the use of data, assist the Virginia Department in setting a vision for student outcomes by reviewing and refining its definition of college and career readiness, as well as focusing on Virginia's early warning systems for middle school and set expectations for what students know and should be able to do in middle schools and beyond. This last bullet is the impetus for this webinar series. We know that numeracy, literacy skills are very important, particularly in the middle school and elementary grades, and we wanted to provide some research-based practices that could help develop better skills in both these areas. So some of the goals of today's webinar is to gain a deeper understanding of why building conceptual understanding of fractions can enhance student learning, as well as becoming familiar with some research-based strategies on effective fractions instruction. As we're going through this event, please feel free to tweet about it. You can use the hashtag RELAP or Appalachia Numeracy, and you can tweet directly at us at REL_Appalachia. So I wanted to go ahead and introduce our speaker for today. Dr. John Woodard is the Dean of the School of Education and Distinguished Professor at the University of Puget Sound in Tacoma, Washington. His areas of expertise include mathematics education for at-risk students, instructional intervention research, and school reform. He has served as a consultant to over 20 school districts and 7 state departments of education, and he was also the chair of the 2012 IES Practice Guide, Improving Mathematical Problem Solving in Grades 4 through 8. He'll be talking to you today about math instruction in the context of Virginia middle schools. So I'm going to head and hand it over to John, and thank you again for taking the time to speak with us.
Thanks a lot, Chris. Let me see if we've got the ball turned over to me. So bear with me for a moment. Oh, there you go. I'm advancing the next slide. We're ready to go. Thanks again for all the attendees who've taken the time to come to this webinar. The basic, thrust of this seminar, as Chris explained, is to draw on pretty high-level research regarding, in this particular case, rational numbers. And it's been a project the funders of REL, the Institute of Education Sciences, have been keen on for quite a while. They've devoted a lot of time to organizing syntheses of research, such as the one we're going to talk about later on in this webinar. And it provides an important framework, stepping stone for events like these or even longer day-to-day presentations. So I'm really happy to be part of it. And as Chris mentioned, I also had the opportunity to engage pretty deeply in this kind of practice guide creation through the problem-solving work that we did for grades 4 through 8. And we've done previous presentations on that for REL over the last year or so. But back to the issue of rational numbers. And this is something that I've been personally involved in working on this area of mathematics for probably 20 years. I've published a middle school curriculum around it. I'm doing professional development work around it. This issue is a recurrent one, as you'll see. And just to kind of give an advanced organizer to a message that will appear at several points throughout this presentation, rational numbers are the gateway to algebra. Algebra is the gateway to success in any kind of higher mathematics and, of course, the world of work as it exists today. So you really can't talk enough about how important this topic is in terms of the way it's taught in schools today. This opening slide, take a moment and let's just sort of absorb the information that's here. Some of it's definitional, but I want to make it a little bit problematic. And in fact, one of the things I was thinking about with this slide in particular, I'm going to be asking you some rhetorical questions, some opportunities to think about what's on each one of these slides rather than just either reading the words or talking through it as if you're processing it the same way that I'm processing it. But from the get-go, we have this right there in the first bullet. It's a ratio of two integers. Okay, well, what does that mean in terms of integers? Well, we can see down in the bottom we have -2 over -2, which if we're conversant with fractions and integers, we realize is equivalent to 1. They're written in the form of A over B, right? And the caveat that's pretty important, that's not equal to 0. So the examples we see move everything, all the way from the left on 1, all the way to the mixed number of 3 1/4 on the right. Now, here's the first question that I want you to think about, and I'll just give you a second or two to kind of ponder it. You've got 1 over 1, 3.25. You could have had 3/4, -3/4. Where's, pi is 22/7? Where would that fit in that stream of rational numbers that you see in blue on the screen? Now, the answer to the question, as you think about it, is inherently important in the first bullet that's up there, the ratio of two integers. Well, teachers may, conveniently say to kids, hey, if you want to remember about what pi is, it's 22/7. Well, the problem is pi isn't a rational number. 22/7 is a shortcut, but it's a misunderstanding of what really is an irrational number. That's what pi is. So one of the things, just from the get-go, with this slide alone, that we have to attend to, the purpose behind the language we see in this slide, is that as we move from whole numbers to rational numbers, we have to start to think very precisely about the kind of numbers we're working with. And in the scope of time that kids will experience, let's just think about this in context. They're moving from first grade, or shall I say kindergarten, up through third grade. They're starting to get introduced more and more to fractions. By the time they're in middle school, then they're going to get irrational numbers. They go up through high school, they get different kind of numbers like imaginary numbers, real numbers. Those are all different kinds of numbers that kids have to keep straight. And this is the starting point for that kind of thinking. This need to be precise, this need to see the kind of variation that you see on the screen in front of you. So while this might just seem very definitional and straightforward, it's an incredibly important slide that orients us toward this shift in thinking about numbers that begins with any kind of formal understanding of rational numbers. We're going to see in the next couple of slides that there's a whole bunch of what kids lack or don't know. I mean, the reason why, and I've said this already, is if you don't have a deep understanding of fractions as you move through middle school, solving problems involving fractions and the computation of fractions becomes difficult. That second bullet is going to be really important as we get most of the way through, or maybe to use a fractional expression, 3/4 of the way through this presentation. That's going to be critical when it comes to understanding what the heck's going on when we do these operations. That's a key piece that's part of today's thinking about fractions instructions in the late elementary grades and the middle grades, conceptually understanding what's going on when we add, subtract, multiply, and divide fractions. And then, of course, as I've said before, fractions are critical to algebra. Algebra, therefore, is the gateway to college and also career success, the numeracy we need in the workforce today. So we're right at a point where we're going to, we mentioned from the beginning there was going to be a poll. And you see the quote up above. I'll give you a second to read it about the coherence and sequential nature. And then I'm going to ask you a question about the poll before we get the poll going. Just take a second. You can read through the paragraph up above. So here's what I want you to think about as you answer the poll. You know, when the poll obviously asks, what percentage of your students struggle with fractions? Well, you know, given where we're going, given what we've said so far, you might be inclined to say, well, 100%, all of them do. What I want you to think about with this question is this particular issue. Think about kids, when you answer this question, what percentage of your students struggle with fractions? Think about kids who appear to at least know procedures, but can't explain what they're doing, what fractions mean, how fractions are different from whole numbers, maybe even have a difficult time connecting what fractions are to, say, what decimals are. So in other words, they demonstrate some kind of procedural competence. They can multiply or divide two fractions, but they struggle to really understand what this is all about, and they can't connect it to other kinds of numbers around them. So let's just take a second. I believe we have about 40 seconds we can do to kind of answer the poll. Looks like we got the results, and we've got a real U distribution. We have, let me see if I can expand this out for a second. 26 to 50%, about 4 out of 10 of you consider that to be a case. Between 51% and 75%, that's about 1 out of 10. And then 75% and above, we've got 4 out of 10 again. So clearly, the majority of you feel that a significant number, and what's a really important statement about this, as I said, I'm kind of qualifying the question. We're not talking about kids who just get lost, who don't know what they're doing, they convert to like denominators when they multiply, they add denominators together when they shouldn't be adding them because they need like denominator. We're not talking about those kinds of kids. We're talking about kids that appear to be, somewhat knowledgeable but can't make the connections, and that's a pretty profound statement. I mean, basically we've got over half of you are above 50% on that particular poll. So let me move on to the next slide. So here's, a problem that I think is very telling. And what I want to focus on with this slide, and again, I'm going to ask you some rhetorical questions about it. I want to give you time to think not about the problem itself, what's the answer to 12 13s plus 7 8s. I want you to think about responses A, B, C, and D. We know that E is the 3 words are the most famous words in, classrooms. I don't know. Why did they put 1 for A, 2 for B, 19 for C, and 21 for D? We know that 24% of 13-year-olds didn't answer it correctly, and 37% of 17-year-olds, 24% could answer it correctly, and 37% of 17-year-olds. But why did they make those choices? Now, you can't answer, and we're not doing polls, but as I walk through them, well, one reason why A might be a compelling answer is that if you add 12 and 7, you get 19. You add 13 and 8, you get 21. Well, 19 21s, that's about 1, of course, and that conveys the fact that you're simply adding numerators and numerators and denominators and denominators. The correct answer, of course, is somewhere around 2, so should be B. Where does the 19 and the 21 come from? Okay, well, of course, 19 would be ignoring the fact that these are a ratio of integers and just doing the 12 plus 7 and stopping there. And of course, the 21 is just looking at the denominators and forgetting about the rest. And this kind of fragmented understanding, I think, my intuition is for why the majority of kids at 13 or 17 cannot answer this kind of thing correctly is because they only know fractions through procedures. Stuff gets confused, it gets lost, and because they're prone to just work on practice problem after practice problem after practice problem without thinking closely about what they're doing, well, it's just a convenient shortcut is, it should be about, 19. Okay, 12 and 7 is 19, next problem, that kind of thing. There isn't this deeper look at what fractions are all about, and of course that's what we're going to try and get to as we go throughout the remainder of the presentation. So, 80% of seventh graders, we can read through the list, could change a mixed number to an improper fraction, but fewer than half knew that 5 1/4 was the same, that they couldn't decompose numbers, right? That 5 1/4 is 5 plus 1/4. You got about a quarter of kids who couldn't shade 1/3 of a rectangle. And this observation is really important. Deborah Ball, who's a big mover and shaker in math education, did her study over a decade ago, probably 2 decades ago, and it was really interesting what she did. All she did was this. Take your typical window pane. You got your rectangle, or basically your square even, and you've divided into 4 smaller squares, right? So you got 4 parts, and you have kids shade a quarter. And 90% of the kids can shade one of those little window panes. And everybody looks like they understand what 1/4 is. Well, what she found was when she gave kids just the rectangle and had them shade 1/4, the shading was all over the place. Kids would be shading 3/4 of the rectangle without that highly prompted structure where you've got the square broken down into 4 equal parts. Without that there, kids didn't know what to do. And so, in some respects, the reason why we're getting such poor abilities on this second bullet is kids have been given relatively simple, highly prompted tasks and not been given other opportunities to think about fractions in a deeper way. The division of word problems is notoriously difficult. It's hard for people to even come up with division problems in fractions. Okay, if you go to the work of Li Ping Ma, who contrasts the way fractions are taught in China versus the way fractions are taught in the United States, they spend a ton of time not only working on division of fractions, what it means conceptually, but also thinking about it through all kinds of real-world contexts. So we'll come to one of those as we get near the end of this presentation. The ordering of fractions, half of the kids couldn't order 2/7, 1/2, 5/9. In our work on particularly decimals, which of course is related to all of this, I find as somebody who teaches graduate students, and that whole notion in statistics of the value being 0.5 or less, so many students, when they get computer results of some kind of statistical test, will take a long time to figure out if the value they have is less or greater than 0.5. Right? This ability to work with fractions and do it in a way, and this is why this 4th bullet is so important, do it in a way that they don't convert to common denominators is a big difference between kids who are proficient in fractions and those who aren't. How do kids, just forget about the 1/2 for a moment, how do kids think about 2/7 and 5/9? Or how would they even think about 2/7 and 2/9? All right, have they been given opportunities to ways to think about different fractions and think about what you're going to see as a really big issue in this presentation, what's called the magnitude of fractions. Okay, and then you've got correctly translating 29 thousandths into its appropriate form. It's clearly very easy, and I would imagine that the common misconception or error that the 17-year-olds would be making would be 29 over 100. Oops. Here we go. And then we get to the issue of taking numbers like 136 over 100 and writing it as a decimal. We get into this idea of converting from decimals and decimals to percents, and it becomes very difficult. Think, for example, about what if kids get a number like 400%? Seems like a huge number. Well, what is it equivalent to as a whole number? It's really only equivalent to 4. If you were to look at these numbers on a number line, it would be startling for kids to make these kinds of conversions. I mean, where would this be on a number line? And this is why, when we get to the research behind fractions, this whole idea of locating these numbers on number lines, having a sense of their magnitude is so critical. This, what looks like a gigantic number, 136 over 100, is pretty much close to 1, between 1 and 2 on a number line. And if you were to ask kids that, based on the information that's just presented on the slide, very few kids would be able to do that kind of thing. So then you, of course, go into where we all get indicted, the adults, right? 3/4 of them can't explain how they compute interest on a loan. That one I have some sympathy with. I mean, if you've ever taken out a house loan like I have, I barely can make my way through the paperwork. I let them do the explaining more than me. So I'll cut them some slack there. But, if this is correct, 7 out of 10 adults can't calculate miles per gallon. That's fairly alarming. And what we do know, anytime we go out to meals with friends or strangers, it's stunning how difficult it is for people to calculate tips, particularly if it's 15%, not to mention 10. One of the things I've noticed, by the way, in the context, I was thinking about this when I was looking at this slide, in the context of cabs now, if you've been in a cab where you can slide your credit card in the machine, it will give you an opportunity to, of course, give a tip. And, talking to a couple cab drivers, virtually no one calculates the tip anymore. They're more than willing to pay 20%, as opposed to the typical 15%, just simply because it's so difficult to figure out the calculation for most people. Taxi cab drivers are making a tremendous amount of money just based on this mathematical problem that most adults have. So, the whole scheme, why it is so hard? Well, think about it from a kid's point of view. We are wired in some respects to count. All of that stuff occurs before preschool. We hit school, it gets formalized, our whole numbers. We work our way through whole numbers. One of the things that we take for granted when we count with whole numbers is that the unit we're counting with is a unit of 1. That's why 4-year-olds know what's beyond 1,000. They know it's 1,000. Some of them know it's 1,001, 1,002. They can count on, and some kids take great pride in doing it. But what they take for granted is that next number is built off of a unit of 1. When you get into the world of fractions, we don't play the game that way. And what comes after 1/3 is not necessarily 2/3. It could be anything that's greater than 1/3 that comes after. It's in a very, very different way, difficult kind of thinking for kids to do, and it's a dramatic change in the way we understand numbers. Not to mention the fact that, going back to the 4-year-old who can realize, well, gosh, you can count on infinitely if we move to the right. Many kids can come up with that realization. What is mind-boggling not only to a middle school student, but even adults, is the idea what's formally called density, that between any two whole numbers, we have an infinite number of fractions. It's a mind-boggling concept when people think about it. It's hard to believe that packed between this discrete space, we have an infinite number of fractions. So it's a whole different way we have to start thinking about it, and we've avoided that simply because it's been easy just to engage kids in procedures. The biggest problem, and I think I can say this starting with this slide moving forward, and I've talked to so many teachers about this, everybody talks about developing the underlying concepts behind fractions. What happens in practice is that stuff is moved over very quickly, and we jump right into operations on fractions if that's the real deal. That everything about fractions has to do with adding, subtracting, multiplying, and dividing. So, the other point that they make, and this is kind of a fascinating one, the whole idea that fractions are just limited to part-whole relationships, that's worth unpacking for a moment. What's important to understand here about the part-whole relationship is if it's made problematic to kids, if we engage kids in thinking, they can be incredibly rich things to do. What I'm talking about here specifically is if we use Cuisenaire rods with kids, we can use a long brown rod and a short red rod. We can constantly redefine what the whole is. We use the range of rods. That opens up a much deeper understanding of part-whole relationships rather than the proverbial circle graph where we have it divided into 4 parts, one of which is colored yellow, the 3 of which are colored red, and the idea is you count up 4 parts and that's your denominator and your yellow is your numerator. If instruction is limited to just that, this is highly problematic, and that's what they're talking about here. Part-whole relationships are incredibly rich. They take a long time to develop, and they are just one part of the underlying concepts that kids need to understand fractions well before they ever get to the operations on fractions. And of course, it makes perfect sense that if teachers have good content knowledge that's correlated, it's going to be correlated with higher student achievement, and this is the very issue that we're kind of addressing. One of the things that's clear with all the standards we look at, irrespective of whether they're state standards or the Common Core standards, whether they are, fractions instruction now is being pushed down much more formally, much more conceptually into the elementary grades, particularly the intermediate grades. So, what they here's what happens. They arrive in middle school. They have a limited sense. They mostly engage in procedures. They get a mishmash of things. One of the things that's probably the most, I'd say there are 2 things that are really important in the context of this slide. One is that kids get superficial treatments of fractional ideas, particularly operations on fractions. And related to that, they don't get task variation. They don't get challenging tasks. And I'm going to give you one coming up here in a little bit about rational numbers that gets them to engage in the deeper ideas behind fractions. And I guess there's another thing that I would add here. One reason why they leave middle school and they still have difficulty is that whatever the representation may happen to be, the way we do curriculum in the United States is we tend not to stick with that representation. What I mean by that is this. This will come up really on the periphery of the presentation in a moment. But if you take a country like the Netherlands that does very well on international assessments, one reason why they do very well, particularly at the elementary grades, is they make a tremendous commitment to the number line as a way of thinking about whole numbers and about fractions. So that long-term commitment to representations, people in Singapore use a variety of representations that they learned from other countries. They didn't develop them themselves, and they stick with those representations. The same thing is true with the Japanese. They stick with representations for a long period of time. They vary the task difficulties so kids get used to thinking about these things in different ways. And in that regard, they have far fewer students who leave middle school with difficulties in computations, conceptual understandings, and connections ultimately to algebra. So here's some data for Virginia middle school students. And I think as we go through this, there are 2 words, or actually 3 words that you'll see repeated throughout it. Need additional practice. The thing I would say about this is let's be very careful about what we mean by practice. Practice is not to be something to connote just giving kids more worksheets so that they become 85 or 90% proficient. Practice, as I said a moment ago, involves task variation. It involves a lot of carefully guided instruction. It involves visual representations. And as we will see, it involves applications to real-world problems. All of that incredibly important as you think through all these different areas, whether it's comparing and ordering, which, by the way, isn't simple as addition, subtraction, multiplication, division. It's another aspect, this magnitude aspect of fractions. Working with decimals is a real interesting task that you can do with kids in terms of task variations for multiplying with decimals. What you can do is take 2 decimal numbers like 5.17 times 0.25, right? And then whatever the product of those 2 decimal numbers are, you show the digits and ask the students to find the decimal point. It's almost unnerving. Kids can't believe that. Well, wait a minute, those are the right digits. How can I even begin to think about the answer? And it's something that entails the use of number sense for figuring out what's going on. So if you take 5.17 times 0.25, let's say. Well, 0.25 is a quarter. A quarter, the answer's got to be somewhere, gosh, less than 2, right? That kind of thinking engages them in the kinds of tasks and the kinds of practice that you see on this slide, and you'll see in the next couple of them. More practice on addition and subtraction, equivalent relationships, again, another really big idea that lies understanding fractions that occurs before operations on fractions, solving problems, mixed numbers, multi-step problems, those kinds of things. And then, of course, we get into the domain of scientific notation, proportional reasoning, and also how it plays out on the coordinate plane and counting as it's described down there. But, the operative piece that you see throughout this is kids need a lot more practice. I would take that to be really code for they need a lot of task variation, visual representations, and problem solving as well. So now we're going to get to the research. And what we're drawing on in this presentation, as I said from the beginning, is one of these IES practice guides. As I was introduced by Chris, I did the work. I was the chair of the panel that did the work on problem solving. So that's just another way of saying I know a lot about how these guides are structured and how they work. And this one, of course, is available. It's online. If you just Google it and go to fractions guide or IES practice guide fractions, it'll come right up. You can download the whole thing as a PDF. The panelists, Sigler's the chair. He's done an enormous amount of work. These are incredibly well-known individuals. What they try to do, Laurie Thompson and Jonathan Ray at the end, they try to involve 2 practitioners on the panel as well as sort of academics with long histories. But you have psychologists here like David Gary and Robert Sigler. Thomas Carpenter has been doing work you may know his work in terms of cognitively guided instruction, among other things. Skip Fennell has been past president of the NCTM. James Lewis has done a lot of NSF work. He's at the University of Nebraska and Okamoto's in California. She does a lot of work on math education. Structure of the practice guides real quickly. So if you do download this, let me just give you a little overlay of how they're all sort of structured. You got recommendations, you got it's written in a way, I think this is sort of 2 important points to make about this slide. They're written in a way that are very practitioner friendly. These are not gigantic academic tomes on a particular topic. The page limit is very strict. The language is meant to communicate to everyday practitioners, and each recommendation in the guide, as we will see them in a moment, is a source of professional development in itself. So they're a starting point for all kinds of study groups, professional development seminars, you name it, to be able to sort of lay all this stuff out. And then, of course, you have this issue of level of evidence I'll talk about. And then another little piece that's kind of nice in this, the roadblocks you run into and what kind of suggestions you can do to address those roadblocks. So on to the recommendations. You're going to see that there are 5 of them here. The first one addresses fractional understanding, and you'll see this in the slides that follow. They kind of occur even from kindergarten onward. The thing that's interesting about this guide is the scope of it, from kindergarten all the way through middle school. And then, of course, helping them understand fractions as numbers, big emphasis on number lines as representational systems. Something that came out of the number 3 that came out of the National Math Panel report in 2008 is this big emphasis on understanding conceptually what's going on behind computational procedures, and we'll get to that and talk about the issues there. And then there are connections, of course, all the way up to ratios and proportions. So ratios, rates, proportional thinking is an interesting little addition to this guide. They didn't want to just stop with fractions by themselves. They wanted to show how that in turn connected to the issues of rates and ratios and proportions. And then finally, they addressed, interestingly enough, the importance of professional development. Let me turn to the right side of the screen, though, this level of scientific evidence. The way these guides work is pretty simple. The expert panelists who you saw on the previous slide initially put together recommendations, what they think are the important ideas or recommendations for teaching fractions. What the other working groups who participate on the guide do is they go off and call the research. They look at, in this case, grades K through 8 to determine, okay, what supports these kinds of recommendations. Sometimes the recommendations remain, sometimes they have to be edited out. But the next step that's really important is, how strong is the evidence? What is the quality of research? And IES has made a point of making the criteria for evidence to be high quality research. So we're talking about the random assignment kind of research, high levels of control, those sorts of things, sometimes quasi-experimental. But for the most part, you're not talking about either idea articles or some study that was conducted with 2 or 3 individuals. Those kinds of studies are not considered. So sometimes you end up with recommendations, as you see on this screen, that are minimal. That doesn't mean they should be discounted. It means the research at this point is pretty tentative. Nonetheless, the panel feels that this is still an important idea to put before practitioners. And of course, the research is always evolving. There's all kinds of funded research going on right now with fractions across the range of kids in schools. But you see that associated with each one of the recommendations, in this case, either minimal or moderate levels of support. And of course, high is the highest that you can go. So with that in mind, we'll sort of start working our way through the different recommendations. Starting with initial fraction concepts. And again, thinking about, we're going to talk about a big span of time and a very short span of time. Big span of time being kindergarten, going through, the end of the primary grades. What they want to do is get kids to, in a way that's sort of problematic, understand the concept of division as it works its way into fractions. That's kind of the big idea that's behind this initial fractions concept recommendation. So, when I was looking at this, it resonated closely with some work we did decades ago. We were working with first grade teachers, and they wanted us to, because we had funding from the U.S. Department of Education to do work with low-achieving kids, they wanted us to help them understand the needs of the lowest kids who were coming into first grade. So, in working with them, we said, look, we'll take a year and we'll just kind of try to understand their progress through school. And one of the things we did with these kids, to make a long story short, is that we asked kids all these word problems. And we had them do pattern analysis and counting, doing all these other things, but we actually gave them word problems. And what we found is virtually all kids had a fundamental concept of division. If you had, let's make the first problem fairly simple, you had 8 pizzas and you wanted to divide them among 4 people, how much would each person get? We found even the lowest achieving kids could do that kind of thing if they had manipulatives, Unifix cubes, chips, whatever they happen to be, available to sort of model the problem. So their starting point is kind of division without remainders, and the whole idea of what division's about, which is how many in each group or how many groups, but then starting to work toward more intuitive models that involve fractional outcomes. So now you're going to take one object and you're going to partition it. And we're moving across time here. We're moving from kindergarten, first grade, second grade, even into third grade as we sort of think about these tasks. So you first partition an object, and that's somewhat intuitive to kids. They've had a pizza. They've seen how it's been shared among certain numbers of people. 4 is an easy number to work with. We can see how each one gets 1/4. Then you start partitioning sets of objects, right? So you have 4 pizzas. That's a little bit more complicated. How does that get organized? How much does each person get? And then, of course, the relative size. And we get 3, 4, 5. And this is going to get to one of the central ideas behind fractions, as they're actually represented 1/2, 1/3, 1/4, 1/5, 1/6, these unit fractions, right? As the denominator increases, the size of the share decreases. This inverse relationship is not intuitive for kids. And then, of course, we get down to this equal shares, 4 pizzas being shared among different people. And the next slide kind of shows this, which group would you rather be in? This slide alone speaks to some very important underlying concepts. I mean, if you were just to take 2 of these pizzas, let's just take the first 2. You have 1/2, one that's divided into halves and one that's divided into thirds. Suppose you took the one that's divided into thirds and made it twice the size. Forget about the 3 that are on the right. You made it twice the size as the one on the left that's divided into half. And you ask the kids, which one would you rather have? Well, most kids would pick 1/3. Why is this display oriented the way it is? Well, part of it depends upon a robust understanding of equal shares. So not only in terms of problematizing as you increase the numbers and the unit, the object is the same, it also has to be the same size. Those kinds of comparisons aren't obvious. You need to have those kinds of variations, those kinds of discussions, so that kids right from the get-go have a richer understanding of what these fractional concepts are all about. The inverse relationship between the number in the denominator and the size of the share, also the importance of equal shares as an underlying concept. And of course, you get these representations this way. We have these equivalent shares that we end up working toward. How do you partition this? How do you divide this stuff up? Notice the variations we have going on here. It's perfectly natural for some kids with 8 people. They're going to start right off the bat. They're going to divide up every one of those pizzas into 8 parts to make sure every person gets a part of each pizza, right? Then you have the other way in which you're going to divide it up into 4s, and everybody gets 2 4s. And then, of course, well, you could take the 4 pizzas and just cut them in half. Now, what do we do with all of this? And this slide, to me, has tremendous meaning in the context of the problem-solving guide that I did. This is a good example of problem-solving, and particularly how kids discuss the difference between different answers to the same problem. Right? I mean, it looks like there's only one right answer here for many kids. How do you come to terms with the fact that each of these answers in its own way is correct? And now we're getting into this issue that's not easy to do right off the bat, the issue of equivalence, right? It's back to equal, area, which would make it equivalent, and how that plays out with these different kinds of representations. So there's a lot here you can see. We're not doing operations on fractions. There's a lot here for kids to work with, think about, as they move across this primary grade spectrum of time. These are very challenging tasks, especially this one where they have to talk about the idea of equivalence in terms of an outcome. This is one of the really big points that's made in the guide, and I think somewhat novel for a lot of people. Sigler, in particular, who was the chair of the panel, has done a lot of research with kids in fractions, and it's based largely on his research that he's come to the position that understanding fractions on a number line is a critical piece that's missing in American curriculum. I mean, again, it gets back to this idea of how we're sort of counting by ones, but also how we deal with partitioning into equal shares those spaces between the whole numbers. And ultimately, it's going to serve as a basis for a conceptual understanding of operations. So what we're doing, and it's coming back to another piece that's in the slide, this kind of where it is on the number line also allows what's called a magnitude comparisons, comparing one fraction to another fraction, whether it's a proper fraction or, in this case, the 1 3/4, an improper fraction, where these things are located on a number line. And the number line is not a trivial deal. It's a fairly abstract concept for a lot of kids. So it's going back to this whole point of sticking with representations and working through them across a variety of concepts. So, there's what we're getting here is, people talk about fractions in 2 ways. Fractions as division and fractions as measurement. And this is a good case of fractions as measurement. We are partitioning very precisely these equal shares, in this case between 0 and 1, and we're partitioning it by 4s, which also gets to the whole issue of counting. But to look at the way number lines can be used, well, we can see that in this 3/4 is greater than 1/4. It's closer to 1. All of that gets us into the idea of equivalence. If we were partitioning another number line, or even the same number line, by another quantity, let's say halves, we could see that 1/2 is equivalent to 2/4. Ultimately, number lines can then be shown, as we'll see, to communicate density. That is, there's a whole bunch of ways, in fact, an infinite number of ways, far too fine-grained to do, actually, by hand, that we can, divide the thing up, have equal share units, and hence communicate the fact that there are an infinite number of fractions between 2 whole numbers. And then, of course, ultimately, as kids get older, we can connect that to negative fractions. And also, in some respects, kind of connect the number line representation to other kinds of representations, say area models, in terms of the way we'll partition and think about equal shares. So, you start with 0/8, you go to 8/8, you label your tick marks. Here's an example of having kids explain their thinking, which one's greater, 3/8 or 5/8. That's a good starting point. You can also find where 3/4 is on the number line, finding out whether that's greater than or less than 7/8. And then this sort of notion of linking all of this to benchmarks. We're going to see in a moment that another way to get kids to think about all the action that's going on the number line, even between 0 and 1, 0, 1, 1/2, important benchmarks for thinking about where things are located and making those kinds of comparisons. So the big point that's being communicated here on number lines is it's a great place in which you can go in considerable depth in terms of thinking about what fractional numbers are and how they compare to not only whole numbers, but also improper fractions. So here's a case in this example, and we've done some work on this with low-achieving kids. We found, contrary to the image that you see on the screen, that sometimes it's better to use two number lines, one above the other, rather than partitioning the same number line in two different ways. That, for struggling students, can be a little confusing to do. But the larger point is, given the same space of 0 to 1, partition both the number lines. And there are a lot of strategies you can use. If you're getting into quarters, like in terms of teaching kids this stuff, this is kind of a critical point, that to learn how to do fourths, we might first, we have to first learn how to sort of partition in half. And then, of course, to get fourths, we get halves of halves. Another task that we can work on with kids is we can partition it in thirds. And then, of course, we do halves of those, and we can get down to 6. You get this kind of practice in partitioning. It's something you cannot take for granted. This is something that takes a long time to develop in kids and why you want to stick with one representation. So the whole idea of partitioning into equal units, which is the equal share idea, is a critical piece when you start to work with number lines and fractions, ultimately building toward an ability to ask the question, which one of these fractions is greater, an issue of magnitude. Another thing, while I'm thinking about this and talking about this particular slide, one other kind of number sense piece using the number line and extending it even further, let's suppose we go from 0 to 1 to 2, we can start to look at the relative size of the numerator and the denominator. Again, another way we can leverage the number line is say, okay, well, how big is the numerator compared to the denominator? In the case of 1/4, the numerator is relatively small compared to the denominator. And of course, when we look at its location on the number line, we can see it's closer to 0. When we think about 3/4, or even a better example being 7/8, we can see that the numerator is relatively big compared to the denominator. If you do that kind of thinking around proper fractions, it's a very short step and a good kind of conversation and dialogue in a classroom to say, oh, 8/8, 9/9, 12/12, 2,000 over 2,000, those numbers are identical. They're all equivalent to 1. And of course, anytime a numerator is greater than a denominator, we're talking about improper fractions. So using benchmarks, using number lines, we have ways of categorizing fractions into ones that are relatively close to 0, relatively close to 1, greater than 1. And then there are ways in which we can take benchmarks further, start talking about how are they close to 1/2. And that's tricky stuff. Just take a look at the second one. Is 2/3 closer to 1 or 0? Take a second. I'm going to give you a few minutes. This is another rhetorical question. Think about the answer to that question. Where is it? Closer to 0? Closer to 1? How would you explain it? How would you think about it? Now, let's just sort of investigate two different responses. Is it closer to 0 or closer to 1? Well, okay. We know it's going to be on the other side, the right side of 1/2, and that'll make it closer to 1. And that's pretty straightforward. Let's just ask the question, is it closer to 1/2 or is it closer to 1? I mean, closer to 0, closer to 1 is pretty straightforward. What about closer to 1/2 or 1? This takes a higher level of thinking. And it gets us to think, well, all right, one way we may have to think about this is, well, where's 1/3 in respect to this? Well, if I can kind of visualize where 1/3 would be, where 2/3 would be, well, wait a minute, those things are going to be symmetrical around the 1/2. In other words, the distance between 1/3 to 1/2 is going to be halfway to 2/3. I know that's a mouthful, but when you think about visualizing this, 1/3 to 1/2 is going to be half the way to 2/3. In other words, it's going to be half the way for another third. Well, that means that's a 1/6. So in other words, the distance from 1/3 to 1/2 is 1/6. The distance from 1/2 to 2/3 is 1/6. So 2/3 is 1/6 of the way from 1/2. 2/3 is 1/3 of the way to 1. Okay? That's not something that's going to develop overnight, but it's a fairly sophisticated way of thinking about how we can use number lines to get to a much deeper level of thinking about fractions, what they are, where they are, and their relative magnitude. And you can do other kinds of exercises that are laid out on this. Where's 5/7 on the number line? What about 7/5? We've inverted that. One of the things, if we work with kids categorically on numbers, we can see right away that 5/7, well, that's a proper fraction. The numerator is smaller than the denominator. Moving up even higher, we know that, well, 5/7 between 3 and 4/7, that's going to be halfway, so 5/7 is going to be beyond 1/2. 7/5, on the other hand, we know right off the bat immediately the numerator is greater than the denominator. That's going to be somewhere to the right of 1. That's all kinds of dialogue, talk around the use of fractions in the context of a visual representation. This is the kind of stuff that needs to occur in classrooms. And here we come to a Japanese representation, and I think this is pretty much makes my case. This is something that looks pretty overwhelming. We're taking one number line down below another number line, we have another number line, all the way down, right? Understanding what this means takes a long time to develop. We're continually partitioning into equal shares, thirds, fourths, fifths. It not only allows us to make comparisons, like 1/3 is the same thing as 2/6 is the same thing as 3/9, but it also allows this fine-grained comparison of 3/9 and 3/10, something, again, that's not intuitive to kids. In fact, kids might be prone very clearly to say, well, 3/10 is going to be bigger than 3/9 because 10 is bigger than 9. Again, we're merging these questions, these dialogues, these more complex tasks with number lines as a representation. I should say, having spent a lot of time in Japan and looking at Japanese math education, they do a tremendous amount of work developing and using a representation like this. This is where the concept of lesson study comes in. And teachers explore the idea, they work it all out, they try it in classrooms, people observe, they refine it, and then they finally feel like a representation like this can be an incredibly useful tool for getting kids to think about fractions. So again, it reinforces the notion, you find something, you stick with it, and you use it in a variety of ways. Okay, represent and translate among different forms of the same number. Okay, this was previously stated. What I want to take us for a moment, this is another rhetorical question. We're going to think about, because, one thing they say in the fractions guide, they're using the term fractions as something that covers all of rational numbers. If we do a really good job teaching fractions, not only the concepts of fractions, but operations on fractions, we're obliged, of course, to connect them with other rational numbers like decimals. So I'm going to walk you through a little exercise here. This is one of these things I told you would be a challenging task. And I want you to do this mentally. You can do this on paper. I'll give you a few minutes to do it. Here we go. Use any amount you want. All I want you to do is create a representation of 3/8. Now again, I encourage you to take this seriously. Either do it in your head, visualize what it would look like, or just do a sketch on a piece of paper. What's 3/8? Represent it. Now, if you're probably over the age of 30 or 40, let's say, in all likelihood, you've drawn some kind of circle, you've partitioned it into 8 parts, and you've probably colored 3. And if you're younger than 30, you might have used a rectangle and done something similar, broke it into 8 parts, and then done 3, colored 3. not terribly challenging, okay? And pretty straightforward for us to be able to do. I want to point out that 3/8, when we convert it to a decimal, and there's no hocus pocus here, nothing up our sleeves, is equivalent to 0.375 or 375 thousandths. What I want you to do, use any model you want, now represent the equivalence of 3/8. In other words, represent 375 thousandths. Now I'm giving you more time on this task because clearly this is much more complicated. Visual representation doesn't come quickly to mind. And for sure, if you tried to resort to the circle, let's say, to somehow partition it in a way like you partitioned it to get 3/8, you're kind of tearing your hair out trying to do it. Now, here's the point I'm trying to make, and it's one about task variation, and it's about how we move back and forth between these different concepts. I don't have a lot of time to spend here. I could talk an awful lot about connecting fractions to decimals. It's obviously something that's not seamless. In fact, for most kids, and this is another problem with American instruction, is, fractions end abruptly and kids say, oh, good Lord, this is great. We're back to whole numbers with some funny little period, right? What is important about this task is it gets us to understand right away that when we convert fractions to decimals, we're playing a different game, that this representation of a rational number is based on another big idea that doesn't exist in fractions, and that is to say it's based on the base 10 system. This is just our launch point for going into the relationships between fractions and decimals and what makes decimals different from fractions. This kind of task problematizes the fact that, yeah, it's really difficult to represent because those little slivers of 1/1000 are really hard to draw, whether it's a rectangle or a circle or whatever it is. And this, in turn, as we talk about the connection between fractions and decimals, helps us understand, for example, why we don't have ones. As we move from hundredths to tenths to ones to tenths, not ones, we're all being driven by the base 10 system. When we connect fractions to decimals, visual representations that are very helpful are things like taking a fraction bar, stretching it out so that you have a rectangle. You've got 10 columns. If we were to do, or if that's assuming it's tenths, but if we were to do something like friendly fractions where we had 6/10ths, you'd have 10 columns stretched out, which we in turn could subdivide into hundreds and use a 100-square grid. There are all kinds of great representations and connections we need to make, but the larger point here is we've got to be very careful and use the kind of thinking we've done with fractions to make the connections between fractions and decimals, talk about the underlying ideas of decimals that in turn allows us to move on and understand how operations on decimals are somewhat similar to what we do with operations on fractions. One of the points that's made in the fraction guide, of course, is making sense of procedures using all these different contexts, the representations I've talked about quite a bit, real-world context, which we'll address. This other point of estimations and predictions is incredibly critical stuff. This will get back to that 12 13ths and whatever it was that we were adding earlier, that making predictions about the outcomes of fractions is quite an important thing to do, as well as addressing misconceptions. So as we move on to the operations on fractions, and we're getting close, we have about 10 more minutes, let's talk for a moment about what teachers tend to jump into somewhat algorithmically and what researchers and math educators want teachers to do in schools today, something that's consistent with what occurs in successful countries around the world when they teach fractions. You can see in this display, and I think this is the way I would translate this more than anything else, fundamental concept of addition. You're adding two groups together to combine them into a set, right? Well, at one level, you can add 1/2, and you can add 1/3, and you can put them together. And if we try to sort of leverage what kids know about whole numbers, we can make a contrast between whole numbers and fractions. Again, with whole numbers, as I said before, if you combine 3 and 4, you're counting in units of 1, and that allows you to do 3 plus 4 is 7, or 300 plus 400 equals 700. We can do all that stuff very easily. When we talk about combining 1/2 and 1/3, We can put those quantities together, but we have no way of talking about them. In the world of mathematics, basically, we cannot be precise in talking about what this combined quantity is all about. So even though we can merge the two, light blue shaded half and third, the only way we can really talk about it with any precision is, of course, to convert it into common denominators. And this is where fraction bars or those kinds of strips can be highly useful, or in this case, your circle diagrams, for converting this kind of thing into common denominator to be able to make sense of what the sum of these two fractions is all about. So in other words, we can start with a whole number comparison, problematize the fact that the reason why we have to change to denominators if we have no way of talking about it. And of course, the same thing applies to subtraction. We have no way of talking precisely about what the outcome is. That's why we need to convert to kind of common denominators. And we show that in this case, the areas that are light blue shaded are the same. It's, of course, just converted into a common denominator. In the case of multiplication of fractions, we can again continue to leverage the contrast with whole numbers. Take any two whole numbers, assuming you're not multiplying by 1 or multiplying by 0. Take 3 times 4 equals 12. Your product is bigger than your two factors. Now, when I was going through school, and I think for many people behind me going through school, nobody ever stopped to talk about the product of two proper fractions like 1/4 and 2/3. What does the 2/12 or 1/6 mean as a product in relationship to the two factors? And as the visual display pretty much points out, why in the world is it smaller than the two factors? I mean, how does that make any sense? Well, your area model, and whether it's put in the context of actually a cake or it's done just with visual representations, we're taking what we have to do in a step-by-step fashion to sort of walk through it. We've got an area size that is, in this case, rectangular to cake. We are going to partition it first into thirds because we're taking, what are we doing when we're multiplying 1/4 times 2/3? We're taking 1/4 of 2/3. So first we do, it's in the middle, we represent what the 2/3 looks like, and then we have to partition it even further as we move to the right into fourths, and what we get is 1/4, what's in blue, of the 2/3. Message here is what I've been saying all along, that we pick these representations, in this case a multiplication of fractions, and we have to stick with this. We have to use these representations not only as visual representations, but in the context of word problems. So I am going to pass out to the class 1/4 of this cake that remains, 2/3 of it. How much am I passing out? Well, I'm passing out 2/12. And we again have to talk about what the representation means. The 2 blue, not in relationship to the pink, but in relationship to the entire cake. That's what we have remaining, 2/12. And the fact that that 2/12 is smaller than both the 1/4 and the 2/3. This is a lot of talk, and I think there's a real big point. Again, working with students on this, we like to think that visual representations are these light bulbs. Things just come on. Oh, I get it now. If you're following what I'm talking about, moving from the whole cake, first partitioning into the thirds, then representing what 2/3 is, then in turn representing what 1/4 of the 2/3 is, that takes a lot of time and well-guided practice for kids to be able to understand what this concept's all about. Now, the big payoff here is it starts to make sense why we're changing denominators when we add and subtract, and why we don't have to worry about that when we multiply fractions. Okay, it starts to make sense in terms of why the procedures are what they are. You know, in the old world of just teaching things in a rote procedural fashion, well, the message was you can add or subtract these fractions if they have the same denominator. Oh, well, no, wait a minute, they've got different denominators, you got to convert them. Okay, I can accept that. Then you get to multiply, and the message is, well, forget about all that converting stuff. Just multiply straight across. And, of course, the message was when you have division, don't ask why, invert and multiply. Well, of course, for a lot of kids, they'll play along, they'll get confused, they'll forget, it won't make sense, and the performance will be poor. Slowing it down, giving visual representations, conceptual guidance will help kids see why You have to convert denominators with subtracting and adding, and you don't have to do so with multiplying, which of course brings us to the most challenging piece for people to understand what this whole division of fractions is all about. And so to get through this fairly quickly, one place that's fairly useful to start is to start with division of whole numbers. Let's just start with dividing 2 by 1/4. In fact, we even put it in the context of a word problem. Suppose you had 2 pounds of meat and you wanted quarter-pound patties. How many quarter-pound patties would you get? Well, you can see where that first bar, which represents 1 pound, is subdivided into fourths, and we can start and we can partition or break up the 2 1 time, 2 times, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times. We get 8 patties. Again, leveraging the difference between division of whole numbers and division of fractions, well, we're getting an outcome that is bigger, not smaller, than what we typically do when we are dividing whole numbers. Again, takes a lot of time. It's something we have to work through. If we were dividing, 1/2, now we're dividing 2 proper fractions, we see that we have things divided. We're starting with the same equal shares. It's starting with 1. In the middle part of that display, we have divided 1/2. How many times will 1/4 go into 1/2? Well, it will partition it 2 times. This is a measurement presentation of division that can help kids see why this outcome of 2 actually makes sense. And as I said before, the predicting and making sense of the reasonableness of the answer, especially if we were to sort of use this in the context of number lines, really helpful in terms of making sense of fractions. Now, proportional reasoning is a piece that they bring up in the guide. This takes us well beyond. This, in many places, is the start of middle school. It's informal reasoning first. You got to work with visual representations, multiple strategies. You're going to see how tables are used. And this is a real critical piece. As you're starting to connect what we know about fractions, what we know about multiplication, to ratios and proportions, using tables as a visual representation is a huge piece. What you see here, in this case of 1 cup of flour for every 8 friends, is what's called a build-up strategy. Kids need to move in their multiplicative thinking by building from 1 to 8, to 2 to 16, to 3 to 24, to 4 to 32. They need a lot of practice on this kind of build-up thing before they do ratios and proportions. This is pretty much part of the informal learning that goes on. Of course, there's a whole bunch of other pieces that's beyond this presentation. Clearly, ratios are not just part-whole relationships, but they're part-part relationships, and that's a whole other discussion in itself. And when we're talking about different strategies, here's a unit ratio strategy. I apologize for the arrows being a little out of whack here, but the idea is 3/9 is equal to something over 21. Well, we can move back and forth on a table. We can move from the left to the right. That's the big piece about what's in the picture in the center is we can start with 3/9. We can move back to 1/3, and then using multiplication, you can see with the arcing, going from 1 to 7 on top and going from 7 times 1 on top and 7 times 3 on the bottom, we see how we generate what are equivalent fractions to help us make this kind of ratio comparison. So, what teachers need to know? There's a whole bunch that they need to know about teaching fractions, especially if we look at what's traditionally embedded in textbooks and working just from textbooks. It's clearly more than procedures. The representations are critical. The guide itself makes a big point about number lines, benchmarks, explaining things in a variety of ways, and especially anticipating the kind of common misconceptions. That can generate a good discussion, daily problems where, hey, a kid answered a fraction problem this way. Does it make sense? If so, why? Why not? And using all that to kind of drive subsequent instruction, what's called formative assessment in the current language of math education. So in wrapping it up, and I'm trying to do this so we allow time for questions here in just a minute or two, fractions I can't underscore enough are critical to algebra. We know that algebra is all part of post-secondary education. This is something that I bring up in presentations all the time. The number one course taken in community college is the number one course that's failed in community college, and that is to say it's algebra. So if you don't know fractions and you don't know algebra, you're not going to make it through post-secondary education. And we know that post-secondary education is critical in the world of work today. And so you need this deeper instruction. to summarize again, as we think about fractions, you think about it in a way where there's all this preceding conceptual knowledge that underlies fractions. All of that then builds into operations on fractions, and then ultimately we have to connect it to other rational numbers like decimals, percents, and the proportional reasoning we just talked about very briefly. And that means that there's, a lot of professional development work that needs to occur so that we do teach conceptually. I think I've just about made it on time in terms of allowing 15, 20 minutes or so for questions. Any questions?
If anyone has any questions for Dr. Woodward, please feel free to enter those into the Q&A panel of WebEx, and we will ask Dr. Woodward to answer for the benefit of all those that are attending. Okay, we have a question, Dr. Woodward. It says, do you think students who struggle with learning math have a difficult time generalizing the segmenting pizzas to candy bars? In other words, would it be better to teach initial concepts using the bar model from the beginning?
I think that, as long as you stick with it, I mean, it's not necessarily the model itself. And the reason why pizzas come up, and there's sort of a good and bad side of it, is it's part of an intuitive experience. So you really don't have to explain the context for doing it. But, you can make the same argument for candy bars themselves. I mean, there's still, if you look back at the slides in the presentation, we're still talking about partitioning one object, and there are different ways to partition it. So, whether it's a rectangle or a circle, you can kind of still move along the same line of thinking regardless. I think the big answer to the question is it's not the representation itself, the candy bar or the pizza. It's really the amount of questioning, the interaction, the potential misconceptions, everything else that's going to come with having to unpack it. So, to go back to that one slide, if you can remember it, where that pizza was broken up by eighths, by fourths, by half, you're going to get the same thing when you break up a candy bar.
Okay, thank you. Any other questions for Dr. Woodward? Well, we are not seeing any other questions at this point. So with that being said, we would like to turn the event back over to Chris Sun, who will briefly explain about our satisfaction feedback survey form and let everyone know how that information is used, and it will be accessible as soon as we close out, or as soon as you close out of the event. So, Chris?
Yep. Thank you, Jennifer, and thank you, Dr. Woodward, for giving your presentation. I'll be honest, I learned a lot about fractions through your presentation, and I hope the participants did as well. One thing that we would like to do is get your feedback from all of our participants about how this webinar went, what you may have learned from it, as well as what we could do better. So this is our stakeholder feedback survey, and we use these on all of our large-scale events and some of our smaller ones to basically understand what can we do to be more helpful for you as stakeholders, practitioners, educators when it comes to research in education. So I believe when you exit out of this screen and the WebEx, you will be given the link to the survey. And if you could please just take a few minutes to answer it. I believe it's maybe a handful of questions. It shouldn't take more than 5 or 10 minutes. We'd really appreciate the feedback as we're developing more of these. We'll actually be having a webinar on literacy around this topic in the next couple of weeks, as well as an in-person event looking at numeracy and literacy. I believe it'll be in Roanoke. So please keep an eye out for those. And again, please feel free to reach out to us. Andrea Muse is the Alliance lead on the Virginia Alliance, and she'd be happy to take any questions or comments you had about this event as well. So again, thank you, John, for giving the presentation. I think.
My pleasure.
So. Actually, if there is one more minute, we got a second question in.
Sure, absolutely.
So we have a question. What are your thoughts about teaching estimation skills? Seems like an underused skill that we don't seem to be spending a lot of time on. I'm thinking in reference.
Go ahead. I'm sorry.
I'm thinking in reference to segmenting the number line into equivalent areas without the structure.
Absolutely. You know, I mean, for example, the whole idea of estimation and location of numbers on number lines, and in some respects, this goes right back to the Dutch that I was talking about earlier. They do a tremendous amount with that, in addition to just the idea of partitioning. So in terms of estimation, and it's all about number sense when you think about it, just take 2 points, take a line, take 2 points, and okay, we'll just start, and we'll just say 0 and 100, right? Well, where is 4 on that kind of a number line? Well, clearly it's going to get jammed all the way down near 0. Well, now let's just cut it in half, right? Where is 4 between 0 and 50? Where's 4 between 0 and 10? Where's 4 between 0 and 5? That estimating that distance using the representation like that, even starting with whole numbers, is a huge piece. So it's not something that's certainly exclusive to fractions alone. But it's, you know, the big idea behind this estimation is it's not some algorithmic calculation. It's a reasoned way of thinking about what numbers mean. And if you're going to use something, you know, like a number line, it's in reference to benchmarks of some kind. Okay? So, yeah, absolutely. All the way from, you know, primary grades up through middle school, that kind of thing is a huge, huge piece.
Wonderful.
And curricula, in fairness, curricula, there have been curricula in the past that have done a lot with that, even with, say, second or third grade kids, where you've got the proverbial jars of marbles, or one of the most, you know, vexing tasks for some kids, that they really do get into it, how many paper clips would fill the room. I mean, it's not even just about coming up with a number, it's about how would you come to thinking about this, how would you unitize this, if a box has so many paper clips in it, then how many you know, that kind of thinking. So it's not only just an outcome, a number, but it's very much part of a process.
Great. Thank you for the insight, and I can definitely agree that it's probably an area that just should be integrated throughout lower grades as they learn these skills. So thank you all again for attending the webinar. We hope to hear your feedback soon enough from the stakeholder feedback survey. And Dr. Woodward, thank you again for giving the presentation.
Yeah, my pleasure. Thank you very much.
Have a good day, everybody.